right, we'll go ahead and get started today. A couple of housekeeping announcements. I know that we are a bit behind with homework according to the syllabus, but I wanted to get through the lecture today and the lecture on Wednesday before assigning that homework. So homework 3 will be released Wednesday afternoon, and it'll be due then that next Wednesday, so within a week. On Monday, next Monday, the 21st, I am going to be at study section, so it'll be a recorded lecture only, meaning that there won't be a Zoom, there won't be an in-person lecture. I will post a recording on the Canvas website for you to watch when it's convenient. Midterms have not been graded yet. That is my first to do after get a couple of other fires off my desk, but they should be done by Wednesday by the time we meet again. I fell a little bit behind on the quizzes too, but please know that there is a quiz available for this week if you choose to participate and get a participation point for that. I have updated the participation points in Canvas, and so don't forget your ways for getting those participation points are asking questions during lecture, asking questions via email, sending me memes, or participating in the quizzes. Regardless of the score that you get on the quiz, I can see that you took the quiz, and so that counts as a participation point. Any questions before we jump into the lecture? All right. So if you remember on Wednesday, we talked about correlation coefficients and simply looking at the association between two interval variables. What we're going to talk about today are regression analyses, and in particular, we're going to talk about simple linear regression. But first, let's talk about statistical models in general. So now that we start getting into regression, we want to talk about models of our data or statistical models. And so any kind of statistics that we do, even the ones that we've already talked about, even those t-tests and ANOVA, we can think about in the context of some response. So this is right, our outcome, equaling some statistical model and then what we call our error, right? And so this is how each sample deviates from our model. Sample or observation differs from our model. So this means that every response can be predicted from the model that we choose to fit the data plus some error. Right? A lot of times when we talk about statistical models, we talk about parameters as a way of defining that statistical model, right? So parameters, we usually denote them using Greek letters, like we've seen the mu and the sigma, and beta is what we commonly see in regression type models. But then our statistics, we use a slightly different annotation. So if you remember and mu designated the population mean, where X bar represented the actual sample mean that we calculated. S in traditional letters equals the standard deviation of our sample. And I'm sorry, my things got a little bit shifted there. But what we do for beta, to designate that it's what we estimate our population to be, parameter to be from our sample data, we give it a cute little hat. So that little caret on top of it, if you're not seeing it because it overlaps, it's this little sign up top that says this is an estimated beta that we've estimated based on the sample data that we're looking at. So the simplest model a lot of times that we can use is simply the mean, right? And so suppose we would like to summarize the number of friends statistics instructors have using the model. Friends of an individual instructor equals some mean that we know, our population mean, plus some error. So mean is that population of mean number of friends for all statistic instructors, right? Our population level data. Mean. If we randomly selected 5 statistics instructors and measured the number of friends that they would have, we could estimate what that mu should be, right? And so if we observed 1, 2, 3, 3, and 4, we would predict that the mean number of friends for statistics instructors is 2.6. So now our model becomes our estimated model, right? Our estimated model. Friends I, we use that subscript I to indicate that number of friends is measured at the individual level, right? And so our mean, we're going to replace with that 2.6 plus some kind of error for that individual as well. So if we want to see how well our model fits the data, we use the term of deviance. And so we talked about deviance when we talked about the mean before, remember? And so our deviance for observation I, or for an individual sample, is the difference between the response observation that we actually saw and the estimated model. And so deviance measures the amount of error in our prediction. So as you could guess, if we're really good at predicting, then our deviance tends to be really small. Right. So again, we're using those lower subscript I's to indicate something that's measured at the individual level. So negative deviance means that the model is greater than the response. And so we overestimate the response. And a positive deviation indicates that the response is greater than the model. So this should look familiar. It's kind of the same concept when we were talking about standard deviation, right? Except here we're saying from our model, which our model could just be that mean that we used before. So just like before, we take those deviants and we square them to get rid of that sign and sum them across all of our observations to get an idea of the fit of the data. So the larger that sum of squares, squared errors, or that sum of our squared deviations is, the more poorly our model fits the data, right? So bigger numbers indicate we're not doing a really good job at predicting. Lower numbers means our model's pretty accurate. And just something to note, sum of squared errors is all relative to the data that you're talking about. You can't compare sum of squares errors for 2 completely different studies or completely different models. So our estimate, going back to our example, where our estimate of the population mean is 2.6, so that is our model, 2.6 friends. We calculate the deviance of each sample from that mean, and we get the sum of squared errors. So the sum of squared errors is that the sum of the deviance squared. And like we saw before, in the simple mean model, this equals what we were calling our sample variance, and the square root represents what we were calling our standard deviation. So let's complicate our model just a little bit more, and we'll talk about linear regression analysis. So what is regression? So it's an analysis that provides a way of describing the distribution of a response or outcome or dependent variable as a function of one or more explanatory or independent variables. So a lot of times we say the verbiage we use here is that the regression of the response variable on the explanatory variable. I always get confused about this wording, so I tend not to use it in text and try to write it a different way, but I wanted to put it here and put it in bold. So if you hear this talking about the regression of a variable on another variable, and it describes the mathematical relationships between that response variable and the explanatory variable. So what we're going to focus on today is what we call simple linear regression. So that's regression assuming that the relationship between a single explanatory variable or a single predictor variable and the response variable is linear. So that should sound familiar to you. It's what we talked about in correlation, and actually simple linear regression and correlation are basically the same test. They will give you the same p-value, but they'll just summarize that association or describe that association in different ways. For multiple linear regression, so the difference between simple and multiple linear regression is that with multiple linear regression, we can put more than one explanatory or predictor variable in our model. And so we still use that same response equals our model plus some kind of error. And this one, we're going to replace model with a regression model. So in simple linear regression, I don't know why everything is scooted over here, postulates that the mean of the response variable y as a function of the explanatory vector x. So what you would see if this weren't overlapping is a mu, and the subscript this time is a y followed by a vertical bar and an x. And so in mathematic terms, whenever we see this vertical bar, we can use the word given to explain the relationship. So here it's the mean of y given x. So meaning that we will predict y based on a particular value of x. And so our model here uses two population coefficients, population parameters, our beta naught and our beta 1, where our beta 1 is related to our predictor variable and our beta naught is not. We call this a regression line. And so the relationship between the response y and the value of the explanatory variables can be written like this, where we've replaced the model with that beta naught plus beta 1 times xi. So in this context, beta naught, we oftentimes call that the intercept of the linear regression model. So the intercept is the mean value of y when x equals 0, right? So going back to our equation, when x equals 0, it cancels out this whole beta 1 as well. And so all that you're left with is this beta naught. And so beta naught is the intercept. It's where the regression line crosses the y-axis. On the other hand, we call the beta 1 the slope of the model. And so slope refers to is the mean change in y when an explanatory variable increases by 1 unit. So this is a really helpful definition when thinking about how to interpret that beta, right? So if y doesn't change with x, so if beta 1 is estimated to be 0, then we don't expect there to be any kind of relationship between x and y. And it really is a way to describe how the response variable is affected by that explanatory variable. And we call them both regression coefficients. And so let's take a look here visually to kind of get the concept down of intercepts and slope. So here on the left-hand side, we have the same intercept. So beta naught would be the same in both of these lines because they both cross the y-axis at the same point. But they have very different slopes. So here in this red line, we can see that as our x changes, increases, our y also increases by a standard amount across the whole spectrum of x that we're observing. Whereas the green line, the green line decreases, so the y value decreases at some steady pace as our x value increases. Likewise, on this graph on the right, we have very different intercepts. All of these lines cross the y-axis at different spots. So we have different intercepts. Beta naughts from our equation. But we have the same slope. So we can tell that they're the same slope because they're parallel to one another. And so it's the same rate of increase for the same change in x. So throughout, right, we change our predictor by this much, right? Then our y's change by the same amount. So my arrows are the same size throughout. So how do we determine the correct values for beta naught and beta 1? We use what we call the methods of least squares. So we want to describe the relationship between the response variable and the explanatory variable with the regression line. How do we decide what's the best line? And so if we look at this example data, with all of the dots being our observations, it's hard to tell just visually looking which is the better line of the three to fit this data. So what we do is we use this method of least squares. And what it does is it simultaneously finds the values of beta naught and beta 1 that minimize the amount of error. So minimize that difference between our predicted values and our actual values. And so they do this by minimizing the sum of the squared errors. Luckily, we never have to do that by hand. It's a little bit grueling. Instead, we let the computer do that and pop out our estimated beta naught and beta 1. Right? So remember, our hat means that's what we've estimated it to be. So we've estimated the beta naught and the beta 1, and we've estimated or predicted this y hat for an individual. So in this example, they're looking at annual advertising budget and album sales. I just like this graphic because it shows you this green line is our fitted line of our data. The blue dots, blue equals our observed data. And our green dots equals our predicted data. So for this blue dot right here, based on our model, we would have predicted the y to be lower, right? And so this difference here is that deviance. Right? Deviance, we also called it error. There's a couple different ways to describe it. And so we're fitting the line, or the computer's fitting the line for us that's minimizing the heights of these lines. Let's take a look at an example, walk us through. So we're looking at for a drug precursor molecule that's extracted from a type of nut. They're commonly contaminated with a fungal toxin that's hard to remove. So we want to understand better the relationship from the amount of this toxin or the amount of this fungus in the nut based on the rainfall at the growing site. And so if we can build a model that predicts how much toxin will be in this nut, then we can use it to evaluate new sites to determine whether the reduction in toxin is worth a heftier price, for instance. And so we're going to assume that there is a linear association between toxin content and rainfall. So again, we could have done a correlation. We could have done a correlation coefficient. We would come to the same conclusion as whether there's a significant linear relationship or not. When we want to use a linear regression or regression model in lieu of a correlation coefficient is oftentimes if we want to make predictions later on. Right, so that correlation coefficient doesn't allow us to make that prediction, right? It doesn't give us the intercept and the slope to make a prediction of what the outcome would be for a given value of our predictor. But regression, simple linear regression does. And so is this an observational, a randomized study if our dependent variable is toxin and our independent variable is rainfall? We weren't able to control the amount of rainfall at these sites, right? That wasn't something we were able to dictate. So this is an observational study. Can we make a cause and effect conclusion? No. No. Can't make. Conclusion since this isn't. So the question is, what's the null and alternative hypothesis? So coming back to this, we would specifically like to determine if there's a linear association between toxin content and rainfall. When we go back here to our descriptions of intercept and slope, our slope is the one that's describing how the response variable is affected by the explanatory variable. So that's going to be our parameter of interest. So when we come back to do our null and alternative hypothesis, our null hypothesis is that the beta 1 equals 0. The slope is equal to 0. And beta, or sorry, our alternative hypothesis is that beta 1 is not equal to 0. So remember our statistical hypotheses. So when I ask for a null and alternative statistical hypothesis, they always are about the population parameters, right? They're not about what you've actually measured in the data. So our betas don't get a little hat in our null and alternative hypothesis. So we have rainfall information and toxin information for a couple of different sites. What we're going to do in GraphPad is we're going to use that XY table again, just like we did for the correlation coefficient, and we're going to set it up in the exact same way. And here we do want to be cognizant of what we put in the X column and what we put in the Y column. So remember, our X column is our predictor, and our Y column is our outcome. And it does matter in linear regression that you designate a predictor and an outcome. Right? And so the same values on the same row. So we could have said this was plot A, plot B, if we had measured it with some kind of designation. We're going to ask for the simple linear regression. Just like when we drew the line for our correlation analysis, we're not going to change any of our defaults. By default, it'll calculate that simple linear regression for us exactly the way we want to. Now looking at the data, it automatically has the line on our graph now. We automatically get a graph that looks like a linear regression line. So we do get results, but I'm clicking here on the graphic right away. And so this is that best fit line for this data to go through. So judging on this, judging that the dots aren't very far away from the line and they're randomly scattered about this line, my guess is that the slope is significant, right? So we do see an increase in toxin as rainfall increases in a steady amount. So if we were doing a figure or a journal article or a report, we would make sure that we labeled our X and Y with a lot of detail, including the units. We may draw the line to show where it would be in this data set. When we go to write it up, we tell the reader what each point represents, a different nut sample from a different region, to distinguish that there's no pairing, that there's 10 points, and then describe what that red line is the best fit linear regression line from the data. So again, identical to what we did with the correlation analysis. We're just using a slightly different approach with a slightly different interpretation. So we get lots of results out from GraphPad to try to show you where to pull data from. So slope is super easy, right? So slope is adequately labeled here, 6.726. Our intercept, remember I said that the intercept in the context that we were talking about before, so in this beta 1, beta naught, and beta 1, it was the value of y where the line intersects the y-axis. So it's the y-intercept in this case. I always struggle to remember that, but guess what? They help us out down here and give that exact model of what we're looking for to help us out. Right. This is 10.57. So our regression model is 6.73 times x plus 10.57. So if we wanted to interpret these coefficients, our intercept, we would say the intercept beta naught equals 10.57 again. So if there was 0 rainfall, we would predict average toxin concentration of 10.57. We don't often interpret the slope. And one of the reasons we don't often interpret a slope is because a lot of times that predictor value being 0 isn't kind of in the realm of possibilities, right? Like, so we're not really going to look at a plot where there's 0 rainfall, right? Because there won't be trees growing if there's 0 rainfall. And so it's nonsensical. We're not going to really do any statistical tests about it. For the slope, remember, we're going to go back to our sorry, our definition. It's the mean change in y when the explanatory variable x increases by 1 unit. So the slope here is the mean change in toxin concentration when the explanatory variable x, or when rainfall increases by 1 unit. And so here my units were centimeters per week, for example. So let's write this out in a little bit more formally. I wanted to show you on the word. So the average toxin concentration increases because it's got a positive sign. So it's in units of the concentration. So micrograms per 100 grams. Rainfall is centimeters week by 1 centimeter per week. That's how we would define slope. The average toxin concentration increases by, and that's our estimate for slope, right? Give it a little hat, that's our estimate. Micrograms per 100 grams when rainfall increases by 1 centimeter per week. And so that's, we write this sentence, or sometimes I like to, not sometimes, as part of this class, I like to present this as a sentence form so that you can kind of understand the magnitude of that relationship and to get your head wrapped around it. For writing this in a methods section, we just say a simple linear regression model was used to predict toxin content in nuts from rainfall. Right? So again, we're saying the type of model that we used, and we're declaring our predicted, our dependent and independent variables, and then including that we use GraphPad Prism. When we go to write the results, so remember in this case, the intercept wasn't of much scientific interest, but we were interested in that slope. So we would say an increase in rainfall is significantly associated with an increase in net toxin concentration. We give the slope, we give its confidence interval, and we give its p-value. And then because we said we wanted to use this for prediction, we may include a sentence that indicates the model. So slope plus the intercept plus the slope times rainfall. So where did I get the confidence interval and the p-value? Let's look back here. Here's our confidence interval for our slope. Oops. And then here's our p-value. Is the slope significantly non-zero. That's the p-value we're interested in. So when it comes to making predictions from that regression equation, it's as simple as plugging and checking numbers. So in this example, we have two sites that we're checking out. One gets 2.05 centimeters per week, and the other one gets 1.25 centimeters per week of rainfall. We want to predict the level of toxin in the two sites and compare. So all we do is set up our model. Remember, this is our model from before. And our X in this case is rainfall. So for site A, we were going to estimate it as 2.05. We just plug that into our equation and multiply out. Likewise, if we wanted to do site B, toxin, we're going to start with that same model, 2 plus 6.73 times rainfall. And this time we're going to replace rainfall with 1.25. 7.6 plus 8.4. So our predicted toxin in the second site would be 19 micrograms, remember, per 100 grams. And so we would then have to decide if this difference between 24.4 and 19, oops, if that was a detrimental difference in toxin that we'd be willing to spend more, or what it would look like there. There's two types of prediction. So we call it either interpolation or extrapolation. So interpolation means that we're predicting based on using a value of that independent variable or that predictor variable that was observed within the observed range. So it's something we measured, right? Where extrapolation means that we've gone out of the range of our predictor variable that we saw to build the model. Right. And so if we look at this graphically, interpolation is this middle part. So we actually feel pretty confident doing prediction in this area because that's the values that we base that linear assumption on, right? We get into a little bit dangerous territory with this extrapolation because we don't know how that line or how that data behaves beyond what we saw, right? Like we could assume that maybe this would at some time plateau, that we couldn't get to more toxin in our nut than the weight of the nut, right? And likewise, that zero doesn't make much sense. And we don't know what we would actually observe if we saw something drastically enough like zero rainfall. So this is safe, and this is more dangerous. A lot of times in pharmaceutical sciences and toxicology, we have to do what we call a reverse calculation. So normally we want to obtain a value of that dependent from the independent variable. However, when we're doing things like a calibration curve, it goes in the opposite direction. So we actually want to predict the value of the independent variable from the dependent variable in our original equation. Right. So again, if we did a standard absorption curve, right? Oh, sorry, where we put in this PABBA standard and looked at absorption across the different levels of that standard and then created a curve here. So in this case, our dependent variable is absorption. How did that happen? And our independent variable is the known concentration that we had. Right, so we may create a standard curve in this way, but what we actually want to do is translate an absorption value we saw for an unknown sample into a concentration. So what we do is we simply rearrange our equation again. So it was absorption equals 0.0023. Sorry. No problem. All I've done here is rearrange that equation using simple algebra, moving things to different sides of the equation. And now we have an unknown sample with an absorption of 0.41. So now if we want to estimate that, Baba micrograms, we're going to go 0.41 minus 0.0023 divided by 0. And so that, again, sorry. And again, let's just double check, make sure we're using interpolation instead of extrapolation, right? So we saw in this case absorption at that 0.41 level and concentration at 20.4. So if we go over here, we did see this in our data set. So this is a pretty safe interpolation. So to summarize, we learned that simple statistical model indicates that the response equals some kind of model plus some sample specific error, so that little underscore I. And with simple linear regression, we only have one predictor. And so the intercept, not always that helpful. It's the value of y when x or your predictor is 0, but that slope oftentimes is what we're really, really interested in. So we're done a little bit early. I'll hang around for a few minutes to see if there are any questions. Next, on Wednesday, we'll go over multiple linear regression when we have more than just one predictor variable. Oh, it looks like